Hey, welcome back to Linear Algebra. In this video lecture, we're going to take a look at section 1.3 about subspaces. Got the objectives written there for you. I want to try to motivate and give a careful definition of what I mean by a subspace. Most of the lecture will be listing a bunch of examples, that I'll try to go into as much detail, proving that they're subspaces as possible, but I'll leave a lot of that work to you, trying to give you the sense of how to go about doing that. You don't need to verify all of the vector space axioms it turns out to show something as a subspace. There's sort of a shorter list, this so-called subgroup test, so we'll state and develop that proof. And then there's one more result in here about intersections of subspaces. That's theorem 1.4, so we'll kind of discuss the proof of that. It's written in the book, but we'll go over it together. Okay, so that's the goal. Let's start by, see if I can reveal. I've got this all pre-written out to go a little bit faster. So here's the main definition of what I mean by a subspace. So if you take a vector space V over field F, that's kind of where we're starting. Then if you have a subset of it, remember a subset is just some elements that are in V, but possibly not all of them. So that's our subset notation. W is a subset of V is how you read that. It's called a subspace, right? So subspace of the vector space if W is itself a vector space under those same operations of vector addition and scalar multiplication. So you're basically thinking about it, it's like a part of V that if you only focus on that part of V, it's still a vector space, okay? So given a subset, one way to check if it's a vector space is to check all 8 axioms, but you actually don't have to check all 8 of them because several of the axioms, things like associativity and commutativity, those hold for all elements of V. So anything that holds for all elements of V is actually going to hold for any element in W too, because W is just a part of V. So we don't have to check all 8 of those axioms. All right, so let's make that a little bit more precise by stating this subgroup test. I'm just going to kind of stop the slide right there. It's a busy slide, but we'll walk through it a little bit on that together. And I've started to write out the proof of it down there. So the book doesn't call this theorem the subspace test, but that's how we can refer to it to each other. So if you take a vector space V over a field F, then this is a criteria. It's an if and only if theorem. So it's a characterization, if you like, of when a subset is a subspace, right? So we just saw the definition of that. The subspace means it's a vector space itself under the same definitions. So this thing is saying that that subset is a subspace if and only if all of the following conditions hold. There are 3 of them. So one of them is that the subset has to contain the 0 vector of the space. So 0 denotes the additive identity in the vector space V, and that has to be an element of W. Whenever you have 2 elements of W and you combine them with vector addition, the result has to land in W. Okay, the word we'll use for that is that it's closed. It's closed under vector addition. And then third, if you take any scalar and an element from W, that scalar multiple of that vector is in W. So W is again closed, but this time I'll say closed under scalar multiplication. So the theorem is really claiming 2 things. If you're a subspace, these 3 conditions are true. That's actually the first part of the proof, and it will be very quick because it's just by definition. But the part of the theorem that we're more interested in and that we'll use more often is that any subset that satisfies these 3 conditions, in fact, has to be a subspace. So that's why it's called the subspace test, because it gives you a checklist, a 3-item checklist. If your subset does 1, 2, and 3, then it has to be a subspace. All right. So in any exercises or exam problems in which you're asked to show some specified subset of a vector space as a subspace, you should be thinking about this theorem. This is the criteria. This is the checklist that you use to do that. Okay, let's walk through the proof real quick. I'm kind of using this little symbol. You might have seen it in other math classes. It just sort of means what I'm assuming the hypothesis that was written first. So let's suppose first that W is a subspace. I've got it written down here. So if W is a subspace, well, then we know that it's a vector space under those operations, right? Under the same operations that make V a vector space. And in the vector space V, the identity element, the additive identity 0, is a unique element. So condition 1 has to hold, right? If W is a vector space under the same operations, then it has to have the same identity. So in particular, that identity has to belong to W. Condition 1 has to hold, right? Likewise, W is a vector space under these operations. So vector addition is an operation on it. Well, then that means that condition 2 has to hold. Because if you take two elements in W and you combine them with the vector addition, well, you have to get an element of W because W is a vector space, right? If the sum of X and Y for X and Y and W weren't in W, then W couldn't be a vector space under those operations. Likewise for 3, right? This just has to hold. If you take a scalar and a vector in W, you have to have the scalar multiple of it land in W because W is a vector space. So 1, 2, and 3, I'm just writing here, they follow from the vector space axioms. They follow from the vector space axioms. Here I wrote particular vector space axiom 3, that's the identity, and the fact that vector addition and scalar multiplications are operations in W. All right, so that's just kind of in order. Why does condition 1 hold? Well, because vector space axiom 3 has to hold in W. Why do 2 and 3 hold? Because W has to have vector addition and scalar multiplication. Okay, so that part of the proof is kind of empty. The work is going the other way. I'm going to have to slide this up, so you can stop the video and go back if you need to refer to the statement of the theorem. But now let's suppose that we have some subset, and it satisfies those 3 conditions. Okay, so it's some subset of V, it's a part of V, and conditions 1, 2, and 3 hold. Well, if we look at the second and third condition, that shows that those operations are operations on W, right? W is closed under addition and scalar multiplication. So W has the same vector space operations that V does. And the first condition literally says that it has a 0 vector. The 0 vector adding to anything, the identity is unique. So we get the third vector space axiom. So we have operations and we have the third vector space axiom. What about some of the other ones? The first, you'll have to refer to these. Just look in your book if you want. I'm doing them by order, but that's commutativity, associativity of addition. This is associativity of scalar multiplication, distributive laws. Those things all hold for all elements of V, right? They hold for all elements of V. So in particular, they're going to hold for all elements of W. Right, so we don't have to check those things because W is closed under addition and scalar multiplication. It has a 0 vector. Well, yeah, of course, vector addition is commutative, it's associative. These associativity and distributive laws hold because they hold in V. Yeah, so if they hold for everything in V, they hold for everything in W. So there's just one more vector space axiom we have to check, the fourth one. Pause the video and check, but we've got 1, 2, 3, skip 4, 5, 6, 7, and 8. We have to check this fourth one. So what's the fourth one? The fourth one is that every vector has an opposite, right? Every vector has something that you can add to it to get the 0 vector. Well, if you give me a vector in W, any vector in W, then by the third property, which we're assuming holds for W, if I take the scalar -1 is a scalar, and I multiply it by my vector, I know I have to get something in W, right? Because the third property holds. But -1 times X is the additive inverse of X. We proved that. That's theorem 1.2, right? Theorem 1.2 says that this thing has the property that when you add X to it, you get 0. That's our X prime in the previous notation. Yeah, so that's the fourth vector space axiom. Every vector in W, I'm calling it X here, every vector in W's inverse is also in W. All right, so that's the end of the proof. If you have those 3 conditions, you have a subspace. Let's use that theorem to look at some examples here. I won't try to hide them. Let's just look one at a time. So this first example, it's actually 2 examples. I'm saying that the set that contains only the 0 vector is a subspace. We'll just think about those criteria, right? Let's think about those criteria. Criteria 1 holds, well, yeah, sure, 0 is an element of that set. Look, you're looking at it. What about criteria 2? The only way to choose elements of this set are just to pick them to be 0. And 0 plus 0 is 0. So criteria 2 holds. And then what about the third criteria? Well, if you multiply any scalar by 0, you get 0. Right? We proved that in theorem 1.2. So this set satisfies the third criteria, so it's a subspace. It's kind of trivial to say that V, but it's important to mention it. V is a subspace of itself. You could check that directly from the definition. V is a subset of V, and it's a vector space under the same operations. Cool. Here, let's look at this second, slightly more interesting example. So take your field F. The vector space I'm talking about is the vector space of n tuples. So F to the n, and take some n tuple. Take X in F to the n, and then let's define, this is my W, if you like. W is defined to be this set, I'm denoting it by F sub X, or F times X. And what is it? It's the set of all scalar multiples of X. The scalar ranges over all scalars in the field. Okay, so sometimes people call that the line through X, but we'll talk about that geometry later. I claim that that's a subspace. So you fix a vector X, right? It's not going to change. It's picked and it's fixed. And then this symbol, Fx, it stands for all scalar multiples of X. And I claim that's a subspace. How to prove it? Well, let's use our criteria. Let's use our criteria. So if we choose the scalar alpha equaling 0, it's the second time in the last minute that we've used this fact, 0 times any vector is the 0 vector, right? So that shows us that the 0 vector belongs to Fx, right? So that's criteria 1. Criteria 1 of our theorem. 0's in there. 0 belongs to this set. To check criteria 2, pick 2 elements of the set. This is how every one of these proofs is going to go. Let something, I'm calling them U and V in this proof, be 2 arbitrary elements of the subset in question. Okay, now in this particular case, what does that subset mean? If I pick U and V in it, it means there have to be some scalars so that U is equal to something times alpha times X and V is equal to beta times X, because that's the definition of this set. All right, now I just look to see if U plus V is in there, so add them together. Take U plus V, rewrite them in the terms of U is alpha X, B is beta X. This is a vector space axiom, right? That's one of our distributive laws, that alpha X plus beta X is alpha plus beta X. And alpha plus beta is certainly an element of F. So that shows by definition that U plus V is an element of F sub X. So there's our second condition. Same thing for the third. If you take some scalar gamma, I'm using gamma because I've already used alpha and beta. So that's the third Greek character, gamma, in the Greek alphabet. If we look at gamma times u, well, that's gamma times alpha x. Vector space axiom says we can reassociate those parentheses. Gamma times alpha is a field element. So that thing belongs to f of x. So there's your third criteria. So this is very typical of the structure of a statement. The proof of a statement: prove such and such is a subspace. Show it's got the 0 vector. Show it's closed under vector addition. Show it's closed under scalar multiplication. Okay, those are the steps. It's a mechanical process. Nice. Notice in order to compute, or in order to carry out rather those steps, I had to do things like I had to understand what is the definition of the set in question, so that when I pick some element of it, I can say something about that element and so on. But the overall structure here is, does it have 0? Is it closed under addition? Is it closed under scalar multiplication? Okay. Look at a little bit of geometry of what we were just talking about here. This is, if you like, a schematic. Well, it's not a schematic picture. If I pick the set F, the field F to be the field of real numbers, then you can visualize the vector space, say R2. It's the set of all ordered pairs of real numbers. That's the good old, I shouldn't call it the XY plane because I'm denoting the vector by X here, but it's the place where you did all your geometry and analytic geometry and calculus, right? The vector space R2 is just the Cartesian plane. And if you pick some vector X in it, here I've drawn it like this thickened black arrow, it's just some vector. It could be the 0 vector, but I picked it to be non-zero. And what is our subspace W? Here I'm using R because the field is the real numbers, R times X. It's the set of all scalar multiples of X, right? So if you imagine this X as this dark arrow, 2 times X would be the arrow in the same direction but twice as long. 3 times X would be the arrow in the same direction but 3 times as long, and so on. So if you actually color code those things, if you visualize this ray that I'm coloring in red, that's the set of alpha X where alpha is greater than 0. Yeah. If you go the other way, you take alpha to be less than 0, then alpha X would be a vector in the exact opposite direction. So this is the vectors that look like alpha X where alpha is less than 0. So this thing, r of x, is usually called the line through x because of this geometric thing. In fact, I chose n equal to 2 in my example, but I didn't need to. If you choose this number to be anything, so Rn, R3, R4, you pick some specific vector, then this is geometrically the set of all scalar multiples of a fixed non-zero vector is a line in that Euclidean space. But I chose n equal to 2 so I could draw this picture. So you're sort of looking at a subspace here. The plane itself is the entire vector space. Yeah, the vector space R2 is the entire plane, and this line through the origin is a subspace of it. And you can imagine that any line through the origin is a subspace of that vector space. Later, a little later, when we develop some theory, we'll show that in a sense, other than R2 and the vector space that contains 0 alone, those are the only subspaces, actually, of this particular vector space. But that's getting a little bit ahead of myself here. Okay, this video is getting a little bit long. Let's keep it going here. I've got more examples. These I'm going to treat really briefly. I'm just kind of establishing, my purpose in this is sort of establishing some notation and then giving you some prompts that you can fill in some details. I hope that when you're watching this video, you're pausing as we go and kind of filling in the details of these 3 things you need to check. Okay, but just to establish the notation, what do I mean by this fancy looking notation, Pn of f? Well, it's the set of all polynomials. Remember, P of f is polynomials with coefficients in f, but I'm going to restrict it, so I'm looking at polynomials of degree less than or equal to n. And I kind of wish that I could just say that, and that's the subspace. But since we don't really have a degree for the 0 polynomial, I'm going to throw it in there in addition. So I'm looking at all polynomials of degree less than or equal to n together with the 0 polynomial. And the claim is that that's subspace. All right, so you can check those 3 criteria. I'm going to leave it as an exercise to you. Criteria number 1 is sort of built in by default, right? The 0 polynomial is in there by definition. So what are you going to have to check? You're going to have to check if you add 2 polynomials of degree less than or equal to n together, do you get something of degree less than or equal to n? How about if you scale something of degree less than or equal to n? Is its degree less than or equal to n? Those are the details to think about in your exercise. Okay, likewise, I kind of want to leave this one to you. You're going to rely on some facts that you learned from calculus, so you don't have to get rigorous about the calculus facts. If you are a veteran of the real analysis course, then you've seen the very rigorous details of this. But if you say denote by C of r, those functions from the real numbers to itself that are continuous. Okay, so if you've had real analysis, you have a very rigorous definition of what I mean by continuous. If you've had a calculus sequence, then you know what I mean intuitively by continuous. Functions that are defined on the entire real line have a limit at every point on the real line, and that limit equals the function value. So continuous function in that sense. And I claim that the continuous functions are a subspace of the set of all functions from the real numbers to itself. So again, kind of just hitting the highlights. I'm not going to write out a proof of this and make the video too long. We can maybe do it in more detail in class. But what would you have to think about? What's the 0 vector? What's the 0 vector? It's the function from the real numbers to the real numbers that is 0 for all possible outputs. Yeah, so it's the constant function 0. That's the 0 vector, and it's continuous, right? All constant functions are continuous. So the 0 vector is in our set, C of r. And then what about the rest of it? In calculus, or if you've had the real analysis course, you've proved this. If you take 2 functions on the real line, both of which are continuous, then so is their sum. The sum of 2 continuous functions is continuous. Yeah. Likewise, if you take a continuous function, f, and you take a real number alpha, the scale, the constant function alpha is a continuous function, and the product of 2 continuous functions is continuous, right? So those familiar facts from calculus: product of 2 continuous functions is continuous, sum of 2 continuous functions is continuous, constant functions are continuous. They together mean that the set of all continuous functions is a subspace. You can think of other subspaces. Think about in calculus, what other kinds of properties of functions? You didn't just study continuous functions in calculus. You studied another class of functions there, and you can ask yourself, is that class of functions a subspace? Yeah, maybe you know what I'm talking about. Okay, continuing along here. The next example I want to do involves a little bit of matrix terminology. I'm assuming you've seen this in Math 241, so I'm going to be pretty brief about this here. But if you give me an M by N matrix, it's hard to read that. Let me clean it up for you on the fly. So M rows and N columns with matrices with entries in F. Then its matrix transpose. That's what I'm defining. This is its notation, A with a superscript T. It's a matrix with N rows and M columns, and the ij entry of that transpose matrix is defined to be the ji entry of A. Okay, so you just literally, to form the transpose of a matrix, the columns of the transpose of A are the rows of A. So the columns of A transpose are the rows of A. So here's just a little example to make that slightly less abstract. Here's a matrix A. It has 2 rows and 1, 2, 3 columns. So its transpose is going to have 3 rows and 2 columns. And how do I form it? Look, I just take the first row of A and I make it the first column of its transpose. I take the second row of A and I make it the second column of its transpose, and so on. So that's what I mean by the transpose of a matrix. We're going to call a matrix symmetric if it's its own transpose, right? So such a matrix would necessarily have to be square. If you transpose a matrix, the number of rows and columns interchange. So if you're going to get that matrix back, that number of row and columns would have to be equal. So this notion of symmetric matrices only makes sense for square matrices. Okay, and the claim is that if you look at the set of square matrices that are symmetric, it's a subspace of the set of all square matrices. Okay, so you can kind of walk through those 3 steps. I'm going to prove this by sort of proving a lemma. This is an exercise in your text that I took, but I'm going to establish that this is a subspace by first sort of establishing this small lemma, that if you take any 2 matrices, they don't even have to be square, so I'm being a little bit more general here, and you take any 2 scalars, if you form this matrix alpha A plus beta B, and you want to look at its transpose, you would get the alpha times the transpose of A plus beta times the transpose of B. Okay, so how to prove such a statement? How to prove this lemma? It's a statement that 2 matrices are equal. Sometimes in mathematics, I get a little preachy when I teach upper division math courses, and I give all kinds of sage advice. So in mathematics, when you're trying to show some things are equal, sometimes you have to ask yourself, like, well, what are the things? Because there are certain ways, right? There's certain ways to show sets are equal. There's certain ways to show functions are equal. Well, there's a way to show matrices are equal. 2 matrices are equal if and only if they have the same entry. So you have to take any ij pair, and I'm going to look at the ij entry of this transpose and try to convince myself that it's the same as the ij entry of the matrix on the right. Right, so that's what I'm doing. So I pick an I and a j. I'm reading this kind of brief. I'm not quantifying my variables very carefully here, but hopefully my comments are making it clear. So I'm taking an I and a j, an I between 1 and m, and a j between 1 and n. I can write it if you want. So I'm looking for every I between 1 and m, and every j between 1 and n. And I start looking at this ij entry of the transpose. Well, by definition, that's the ji entry of the matrix, right? Because transpose reverses rows and columns. And then by the definition of matrix addition, when you take the ji entry of a sum, you take the ji entry of each matrix individually and add them together. That's how we add matrices. And likewise, by the definition of scalar multiplication, the ji entry of alpha A is just alpha times the ji entry of A. So it looks like I'm just manipulating symbols around here, but each one of them is justified by the definitions. This is the same thing for B, right? And now the transpose definition again, the ji entry of A is the ij entry of A's transpose. Same for B. Matrix addition, again, says that if you have 2 matrices like this, you're adding their ij entries, well, that's exactly the definition of the ij entry of their sum. Okay, so at the end of the day, this matrix alpha A plus beta B's transpose, its ij entry is the same as the ij entry of A alpha times A transpose plus beta times B transpose. So that proves the lemma. All right, how does that lemma prove that symmetric matrices are a subspace? Well, I'm going to leave that to you. But clearly the zero matrix, the matrix all of whose entries are zero, is symmetric. And then think about what this lemma says. If you add two symmetric matrices, can you imagine taking alpha and beta to be 1? And imagine that A and B are symmetric. A and B satisfy their own transpose. Well, when you take A plus B transpose, you're going to get A transpose plus B transpose. But if A and B are symmetric, that's going to be A plus B. Yeah, so the transpose of a sum is going to be the same. Same for scalar multiples. So I'm going to leave it as an exercise to you to prove that this is a subspace, checking conditions 1, 2, and 3. And my hint is that this lemma will make conditions particularly 2 and 3 easy to check. Okay, I'm going fast, but you can stop and take a breath. Here, we've done a lot of examples of something that's a subspace. Let's do an example of something that's not. Okay, so here I've got W. It's the set of 2 by 2 matrices with real numbers, so it's kind of a more concrete example. And the condition to be in W is that the sum of the diagonal entries, A11 and A12, has to be 1. And that's not a subspace. There's lots of ways to see that that's true. But for example, the identity, the 2 by 2 zero matrix, it's not in W. It's not in W because, well, 0 plus 0, its two diagonal entries don't sum to equal 1. Yeah, that's one way to see it. Another way to see it, it's not closed. You don't have to give more than one reason, but I'm saying when you're trying to show something's not a subspace, it suffices to find one criteria that fails. Yeah, because all three of those things have to hold. In this case, I think all three criteria are going to fail. Like, look, here's a matrix that's in W, isn't it? Oops, no, it's not. Excuse me. This one is. That matrix, to check if you're in W, you're just summing these diagonal entries and seeing if you get 1. 1 plus 0 is 1. So that's an element of W. So is this one. Yeah, 0 plus 1 is also 1. But if you add those matrices together, their result isn't in W. W is not closed. Yeah, I think you can easily imagine why W isn't closed under scalar multiplication either. The scalar multiple of that matrix in W doesn't belong to W. You don't have to check all three things here. Just one will do, but I'm just trying to give you examples of if something's not a subspace. This is my favorite way. If somebody hands me a subset and asks me, is it a subspace or not? It's like an open-ended question. The first thing I try to check is if the zero vector's in it. If the zero vector is not in your subspace, then or your subset, then it can't be a subspace. And that's usually kind of an easy criteria to check. This is just for some homework. That thing we just looked at, the sum of the diagonals, that's called the trace of a matrix. So maybe you saw this in lower division linear algebra, but just to sort of throw it in here, if you take any matrix, square matrix, take a matrix whose rows and columns are the same, its trace, which is denoted by just truncating the word trace, TR of A, trace of A, it's the sum of the main diagonal entries of A. So you just add the entries along the main diagonal. So if you're kind of visualizing that, I won't write out this whole matrix, but its entries are A11, A12, and so on, A21, A22, and so on. The last one down here would be ANN. The trace is the sum of just the entries that are along the main diagonal. All right, so what we were just looking at above was our W, if I scroll back, I know scrolling isn't all that fun to watch in a video here, but I could re-describe this set W. These are those elements of M2 whose trace is equal to 1. And that's not a subspace. Okay, last thing I want to discuss, I'll make it brief. This video is kind of long. Theorem 1.4, if you take two subspaces, W1 and W2, we'll just use some subscripts to denote two subspaces of the same vector space, their intersection, the set of elements that are in common to W1 and W2 are a subspace. Why is that true? Well, because W1 and W2 are subspaces, we know that 0 is in both of them. Yeah, so 0 is in the intersection. When you're arguing about intersections of two sets, it's always about arguing about them both. Or think about closure. If we took, say, X and Y in the intersection, well, then X and Y are in both sets individually, right? But W1's a subspace. W1's a subspace, so it's closed. W2 is a subspace, so it's closed. But that means that X plus Y is in both, so X plus Y is in the intersection. So the intersection is closed. Scalar multiplication is treated the same way. Oops. I'm going to leave it to you. This proof is written in your book, so I'm being a little brief. Come to my office hours or bring it up in class if you want to talk about working with intersections, but that's some set theory that I'm going to have you think about in this, okay? All right, so the last thing I'm going to do is kind of leave an open-ended question. The intersection of two subspaces is a subspace. What about their union? I'm not going to answer this question. I'm just going to pose it. But what about their union? Is that a subspace? Take two subspaces. Think about the three criteria if you just want to go for it abstractly. Or if you want to think about in terms of a concrete example, maybe you could try to choose back. Remember in our R2, we had some examples of subspaces. We said if you take lines through the origin, so maybe you could choose some specific vector like 1, 1, and then draw a line through the origin, and then choose some other specific vector, I don't know, like 1, 3, draw a line through it. So you can imagine what their union looks like. The union is all the points that are on one of those lines or the other, or both. There's one point in their union. It looks like 0 is in their union. Is it a subspace? Well, so maybe you can come into my office hour and tell me. Okay, thanks for listening.